It's me again, Isaac Newton. In the 1600s, I was convinced light was made up of particles which I called corpuscles. I really had to duke it out with a Dutch physicist named Christian Huygens, who insisted that light existed as waves.
Huygens versus Newton!
Waves! Particles! Waves! Particles!
And then later, I, J.C. Maxwell, resolved it with my electromagnetic wave theory, saying light exists solely as waves.
But as physicists dug deeper into the atom, experiments made it increasingly clear that tiny particles at the subatomic level behave differently than objects in the visible world. A new set of mechanical equations was needed to describe these quantum mechanics. In one experiment, physicist Philippe Lenard was using lights of varying intensities to blast electrons off a sheet of metal. Atoms on the surface of the metal absorb small amounts of energy, causing some electrons to fly off. According to the classical wave theory, the brighter or more intense the light was, the stronger the light waves would be.
I've got the light on full power, but the energy of the ejected electrons is next to nothing.
But then, when Lenard tried using light with a higher frequency,
Holy flying electrons!
a young German fellow by the name of Albert Einstein came along to take a look.
The only explanation for this photoelectric effect is that light has particle-like properties. But relying on Planck's constant, I prefer to think of light as small bundles of energy, which I will call photons. It doesn't matter how bright the beams of light are, photons have more energy at higher frequencies, not higher intensities.
But Einstein didn't stop there. He went on to say that light actually possessed wave-like and particle-like properties.
Now hold it right there, Buster.
Yeah, we already said that energy had to exist as one or the other. How can light be both?
Not just light, monsieur, but matter as well. Pardon me.
The French prince and physicist Louis de Broglie generalized Einstein's principle, applying it to the entire physical world.
Electrons, protons, photons, tout le monde. Everything has a dual nature.
De Broglie also proposed that electrons themselves exhibited wave-like behavior. These pilot waves adjust their wavelengths periodically, just enough to fit the electron into a stable orbit of a fixed radii from the nucleus. Only objects of a very small mass, like electrons, have noticeable wavelengths, because Planck's constant, h, is such a very small number. For the record, the value of h, which Planck realized could never equal 0, turned out to be 0.0000000, 19 more zeros, 6626. Unquestionably small, but not zero. It took a reclusive mathematician named Paul Dirac to finally settle the particle-wave dispute. Crunching a ton of numbers and equations, Dirac proved mathematically the dual nature of light and matter. Since that time, the wave-particle duality has been free of paradox for anybody genius enough to follow the math.
Particles! Waves! Particles! Waves!
Gentlemen, please. You're both right.